NASA is currently tracking 1,717 near-Earth objects that are considered potentially hazardous asteroids due to their size and orbits. Approximately 70% of the Earth's surface is covered by oceans, so an asteroid is most likely to impact the water. An ocean impact within 10 to 20 kilometers of a populated coastline would be devastating, causing severe flooding, destructive shock waves in the air, high temperatures, and hurricane-force winds. The threat from an ocean impact far from land is more difficult to assess. In particular, we want to know if destructive waves created by an impact can travel long distances to populated shorelines. To understand these threats, NASA held the Second International Workshop on Asteroid Threat Assessment, focusing on asteroid-generated tsunamis.
As part of this effort, scientists from Los Alamos National Laboratory are using high-performance computing to investigate how an asteroid's kinetic energy is transferred to the atmosphere and ocean.
Los Alamos scientists ran an ensemble of 3D simulations, varying the asteroid's size, the angle of impact, and whether or not the asteroid exploded in an airburst before impact. The height of this airburst was also varied. We used X-RAGE, a parallel multiphysics Eulerian hydrodynamics code. X-RAGE uses adaptive mesh refinement to continually subdivide computational cells in important areas, applying more computing power to where it's needed. Our simulations contain 3 materials: a basalt asteroid, static air, and static water. Initially, all kinetic energy is assigned to the asteroid. By studying different runs from the ensemble, we see the effects of varying asteroid size, angle of impact, and airburst. Here, a light-colored pressure wave shows the asteroid's effect on the atmosphere. In addition, a large plume of water rises from the largest asteroid impact. Clearly, more kinetic energy is transferred to the water in this simulation. Slicing through the dataset reveals more detail. The largest impact simulation shows development of a transient crater and a large plume of water and water vapor. Here we see 2 cases varying asteroid size. On the right are plots showing the transfer of kinetic energy from the asteroid to the water and air. Pressure waves in both the air and water show differences in the transfer of kinetic energy. Colliding shock waves in the atmosphere and water, as well as the wind at the water's surface, hinder the creation of a propagating wave. Here we see the difference in energy transfer with and without an airburst. Whether or not there is an airburst changes how much kinetic energy is transferred to the air and water. An airburst breaks the asteroid apart so that much of it skims the surface of the water rather than slamming into it. For the same size of asteroid, this results in a much smaller effect on the ocean. Interestingly, there is a stronger wave interference in the direct impact simulation, but such an impact is more likely to create a tsunami because of the greater height of the splash. This may indicate that a tsunami is more likely to be formed during a direct impact than an airburst. Previous simulations had led us to believe that the opposite was true. A feature discovered through this visualization is a pressure enhancement uprange of airburst impacts. 2 pressure waves combine to create this, one from the asteroid in its trajectory, and one from the explosion when the asteroid material hits the water. This may affect wave propagation and will have to be studied. By visualizing just the water in an impact simulation, we can study the formation of the tsunami wave. Immediately upon impact, a transient crater is created, and a splash curtain is thrown high into the air. Water rushes into the crater, forming a water jet, which can be several kilometers high. This jet collapses to form a rim wave, which is hundreds of meters high. A new water jet begins to form, which will in turn create a new rim wave, a process that continues for some time. Each of these rim waves has the potential to become a tsunami. A threat of equal importance is the plume of water and water vapor that is lofted into the atmosphere. A large fraction of the asteroid's kinetic energy goes into vaporizing water to create the transient crater. Much of the water vapor is lofted into the stratosphere, where it may linger for months to years. Because water vapor is a potent greenhouse gas, this may have significant effects on climate. It is critical to understand the quantity and behavior of this vapor in order to assess the threat it poses. Analysis and visualization of this ensemble of X-ray simulations is already bringing us new insights into the science of asteroid-ocean impact. These visualizations provide new insights and help Los Alamos scientists communicate their findings to peers at the International Workshop on Asteroid Threat Assessment, focusing this year on asteroid-generated tsunamis.